Hello everybody, Math Hobo here, and today I will be talking about why e, Euler's number, is equal to the limit of x tending to infinity of 1 plus 1 divided by x whole to the power of x. And before I talk about why e is defined this way, I'll first need to clarify two fundamental calculus concepts. The first one is the definition of a derivative. Most of you would know the definition of a derivative to be defined as the limit of h tending to 0 of f of x plus h minus f of x divided by h. I will be using a slightly different definition, and we can derive this definition. So let's say I had a function called f of x, and I wanted to find the derivative at some x value a, which is the slope of the line at that point. And let's say I take another x value called x, which is a very small distance away from our first value, and let's try and find the rise and the run of this tiny triangle that we have here. Let me enlarge this triangle. So we have the rise, which is equal to the f of x minus f of a. And then we have the run, which equals x minus a. And if you want to get the slope, you simply divide the rise by the run, and you get f of x minus f of a divided by x minus a. Now, to become very, very precise in our definition for slope, we'll have to take the limit of x going really, really close to a. So we will rewrite this as limit x tending to a of f of x minus f of a divided by x minus a. And this is our new definition of the derivative, and I'm going to call this f prime of a. Now, I will talk about my second calculus concept, which is something called L'Hopital's rule. And it's a French name. And this rule enables us to solve limits that have really weird solutions. They're called indeterminate forms, which turn out to be things like 0 divided by 0, or infinity divided by infinity, which look very interesting but are very hard to determine. Today I will be proving L'Hopital's rule only for the first case, which is 0 by 0, so let's forget about infinity by infinity for a minute. Now, what L'Hopital's rule starts with is the limit of x tending to some value a of our first function, f of x, divided by another function, g of x. And one thing that I'm going to start with is that f of a is equal to g of a, which is equal to 0. So both f of a and g of a equal 0, which is why when you plug in a for x in both the numerator and the denominator, you end up with 0 divided by 0, which is an indeterminate form and is wrong. So how do we find the solution for this? What we start with is we say limit x tending to a of f of x by g of x is equal to the limit x tending to a of f of x minus f of a divided by g of x minus g of a. Our space is getting a little crowded here, so I'll erase our definition of the derivative for now. And you might be asking, well, why is this true? You're just adding some new interesting terms. Well, it's because f of a and g of a both equal 0, so we can add or subtract them. And now what we're going to do is we're going to divide both the numerator and the denominator by x minus a. So then we get this. Limit x tending to a of f of x minus f of a divided by x minus a. And that's only the numerator. All of that divided by g of x minus g of a divided by x minus a. And you might say, well, this looks a little familiar. It's because that's the definition of the derivative that I just erased. And we could plug this back in, and we could say that the limit of x tending to a of this thing is going to be f prime of x, and this thing is going to be g prime of x. So this is equal to limit x tending to a of f prime of x divided by the g prime of x, which is really wonderful because now we've established that limit x tending to some value a of f of x by g of x is equal to limit x tending to the same a of the derivative of f of x by the derivative of g of x. And this turns out to be really useful in our initial problem, which is the definition of Euler's number. So let's get to solving that. Now, the first step that I'm going to take is I'm going to say y, some variable, is equal to the limit of x tending to infinity of 1 plus 1 divided by x whole to the power of x. And you could traditionally evaluate this limit, which would be naively plugging in infinity for x, and you would get 1 divided by infinity, which is 0, and 1 plus 0 is equal to 1. So then you'd have 1 to the power of infinity, which, as we all know, is 1. And we can tell, evidently, that limit x tending to infinity of this function does not equal 1, it equals e. So today I will prove to you why it equals e. So the next step that we're going to take is we're going to say, I'm going to take the natural log on both sides of this equation. So then I get ln of y is equal to ln of the limit x tending to infinity of 1 plus 1 divided by x whole to the power of x. And I can now pull this ln inside of the limit, and I'm going to rewrite this with the natural log inside of the limit, and I get natural log of y is equal to the limit x tending to infinity of the natural log of 1 plus 1 divided by x whole to the power of x. And for those of you who know your properties of logarithms, you would know that this exponent x over here can be rewritten as the coefficient of the entire logarithm. So what we can now say is this ln y equals to the limit of x tending to infinity of x multiplied by ln of 1 plus 1 divided by x. And now you might be saying, Math Hobo, how come we're not using L'Hopital's rule yet? And my answer to that would be, you don't have an f of x divided by a g of x. You only have an f of x multiplied by a g of x. So what I'm going to do here is a little weird. I'm going to say that this is equal to my limit x tending to infinity of natural log of 1 plus 1 divided by x divided by 1 divided by x. So what I did here was I rewrote my coefficient x as divided by 1 divided by x. And I did this because now we have an f of x and a g of x. And f of x is divided by g of x. So now I can use L'Hopital's rule. And I'm going to erase this to get some more space on the board. So what we now can do is we can take the derivative of the numerator and the derivative of the denominator. So what do we get when we take the derivative of ln of 1 plus 1 by x? Well, we get the derivative of ln this. It's a composite function, so we're going to have to use the chain rule. And you get 1 divided by 1 plus 1 by x. All of that multiplied by the derivative of the inner function, which is 1 divided by x, which is negative x to the power of negative 2. And I'm going to replace the 1 with that. So I'm going to say negative x to the power of negative 2. And that's only our numerator. Now we have to take the derivative of 1 divided by x. So I'm going to divide this entire thing by the derivative of x to the power of negative 1, which is negative x to the power of negative 2. And this same limit still applies. So it's limit x tending to infinity of negative x to the negative 2 divided by 1 plus 1 by x divided by negative x divided by negative 2. And if you know your maths properly, you can divide these two off, and then what do you get? You get is equal to limit x tending to infinity of 1 divided by 1 plus 1 by x. And now we can do the simple thing. We can plug in x is equal to infinity over here. And what do we get? 1 divided by infinity, as we all know, is 0. And 1 plus 0 is 1. So 1 divided by 1 is equal to 1. And now we're going to retrace our steps back, and we're going to go back to our second step, I believe. And we're going to say this is equal to the natural log of y, and which is equal to 1, as we have evaluated. So now I have ln y is equal to 1. So what is y? Y, of course, is equal to e. And now I can plug in my original definition for y, which is limit x tending to infinity of 1 plus 1 by x whole to the power of x, and that equals e. And wonderful, we have now demonstrated why Euler's number is defined in such a mysterious way. So that is Q, E, D. Thank you very much.